In Year 1, we learnt that enthalpy was the heat content stored within a chemical system, and that chemical changes are associated with changes in enthalpy. As a result, energy in the form of heat is either released to the surroundings by the system, in the case of exothermic changes, or is absorbed from the surroundings by the system, in the case of endothermic changes, during chemical processes. We will now introduce the idea of standard lattice enthalpy, which is defined as the enthalpy change that results in forming 1 mole of ionic lattice from its gaseous ions under standard conditions. Lattice enthalpies give a measure of how strong the bonds are within an ionic compound, and are useful in explaining differences in melting points between ionic compounds. The more energy that is released in forming the ionic compound from its gaseous ions, the more stable the compound and the stronger the ionic bonds within the lattice, and so the higher the melting point. It is not possible to measure lattice enthalpies directly experimentally, in the same way it was often not possible to measure standard enthalpy of formation values that we came across in Year 1. It is possible, however, to theoretically calculate their values from information found in chemistry databooks. What we do is construct Born-Haber cycles, which use the ideas of Hess's law that we came across in Year 1, where if a system undergoes the same change via 2 different routes, providing the starting and end points are the same, the enthalpy changes via the 2 different routes are the same. Let's look at the Born-Haber cycle for calculating the lattice enthalpy of potassium oxide. What we are interested in is the enthalpy change when we form 1 mole of ionic lattice from its gaseous ions. This is a highly exothermic change, since very strong ionic bonds are being formed with the associated release of energy. If we remember, breaking bonds requires an input of energy and so is endothermic, whereas forming bonds releases energy and so is exothermic. Now let's start with the elements as we find them under standard conditions in their standard states. The enthalpy change in forming the ionic lattice from its elements in their standard states we have come across before as the standard enthalpy of formation, and we can look this up for potassium oxide and add this to our Born-Haber cycle. We need to find the enthalpy change in turning our elements in their standard states to gaseous ions. We do this by working out each energy step in turn. We first look at the enthalpy change in changing solid metallic potassium to gaseous atoms. We will need to input a significant amount of energy to do this to overcome the metallic bonding, and therefore the change is an endothermic one. We can look this value up in data tables as the enthalpy change of atomization, which gives us the energy change to form 1 mole of gaseous atoms. In this case, we need to form 2 moles of gaseous atoms, and so the enthalpy change of atomization needs to be multiplied by 2. Now we need to atomize our oxygen molecule. This will involve breaking the covalent bond and will require an input of energy. The enthalpy of atomization for oxygen is endothermic at plus 249 kilojoules per mole. Now we have our elements as atomized gases. We need to now form the ions. For the potassium, we need to remove an electron. This is an endothermic process, as the attractive force of the nucleus has to be overcome. If we remember, the energy change when 1 mole of electrons is removed from 1 mole of gaseous atoms is the first ionization energy. In this case, we have 2 moles of potassium atoms, and so we need to double the first ionization energy. Now we need to add 2 electrons to the oxygen atom to form the 2- ion. We do this 1 electron at a time. The oxygen atom will readily accept the first electron, as it will be attracted to the positively charged nucleus, and the singly negatively charged oxygen ion will end up lower in energy, and so this step is exothermic, and energy is released. The energy associated with gaining the first electron is known as the first electron affinity, and the first electron affinity value for oxygen is minus 141 kilojoules per mole. Now to add the second electron to an already negatively charged ion is going to require energy to be added to overcome the repulsive force of the negatively charged electron being added to a negatively charged ion. The second electron affinity for oxygen is endothermic at plus 744 kilojoules per mole. Now we have gone from our elements in their standard states to the gaseous ions, and the only step missing in our cycle is the lattice enthalpy, which we can calculate by applying Hess's law. If we total up all the enthalpies/energies going clockwise to reach the ionic lattice, starting from our elements in their standard states, and we do the same going anti-clockwise, Hess's law tells us that the clockwise route will equal the anti-clockwise route. And so we can take all our values for the clockwise route and add them together. We now do the same for the anti-clockwise route, and since the anti-clockwise route will equal the clockwise route, we can set it out as follows. Now we need to rearrange to make the lattice enthalpy the subject. We can do this by subtracting it from both sides of the equation. We can take away minus 363 kilojoules per mole from both sides. Now we can enter this long string of enthalpy changes into the calculator exactly as it is written here. If we do this, we obtain a value of plus 2233 kilojoules per mole for the negative of the lattice enthalpy for potassium oxide. If we multiply both sides by -1, which means we change the sign of both sides, and then the lattice enthalpy for potassium oxide comes out to be negative 2233 kilojoules per mole.